Welcome to the 8D Sleep Lab. Before we begin, please ensure you are wearing headphones. This experience uses 8D audio technology designed to move the sound around you in a soothing circle. Tonight, we have selected a process that is famously slow, predictable, and deeply satisfying. We will be following the industrial manufacturing cycle of wax crayons. There is no plot to follow. There is no ending to reach. There is only the rhythm of the machinery and the flow of the wax. Find a comfortable position. Unclench your jaw. Let your shoulders drop. Close your eyes. Let us enter the factory. Chapter 1. The Paraffin Silos. The trucks arrive in the pre-dawn hours when the air is still cold and the gravel lot is empty. They are unmarked, industrial tankers, their cylindrical bodies painted a dull white that has yellowed with road dust and exhaust residue. The engines idle with a low mechanical rumble that vibrates through the chassis and into the ground beneath. Each truck carries 11,000 gallons of molten paraffin wax heated to precisely 147 degrees Fahrenheit. The driver descends from the cab. His boots make a hollow sound on the metal step. He walks to the rear of the tanker where a thick rubber hose hangs coiled on a steel hook, and he lifts it with both hands. The hose is warm to the touch, heated from within by the liquid it will soon carry. He drags it across the asphalt, the rubber scraping with a dull, repetitive friction, until he reaches the intake valve embedded in the concrete pad. The valve is circular, 12 inches in diameter, with a threaded bronze cap that has oxidized to a pale green. He removes the cap by turning it counterclockwise, 7 full rotations, and sets it on the ground beside his left boot. Beneath the cap is a dark opening, a throat of machined steel that descends 30 feet into the earth, where it joins the main arterial pipe leading to silo number 3. He attaches the hose. The coupling clicks into place with a metallic snap that echoes faintly against the corrugated walls of the storage building. He returns to the truck and opens the discharge valve, a heavy lever that requires his full weight to turn. There is a pause, a moment of silence, and then the pump engages. The sound begins as a deep hydraulic groan, a mechanical exhalation that rises from the belly of the tanker. It is a sound without melody, without variation, a single sustained note of industrial effort. The hose stiffens as the wax begins to flow. You can see it swell slightly, the rubber expanding as the pressurized liquid pushes through. And if you place your hand on the hose, you can feel the warmth radiating through the thick black skin. Inside the pipe, the paraffin moves in a slow, viscous current. It is translucent, like rendered fat or melted candle drippings, and it flows with a weight that is both liquid and something heavier, something that resists the pull of gravity even as it yields to it. The pipe descends at a 17-degree angle, sloping down into the earth. And the wax follows this path without hesitation, without turbulence, a river of warmth moving through cold steel. Silo number 3 stands 60 feet tall. It is a cylinder of brushed aluminum, seamless and featureless except for the riveted seams that run in vertical lines from base to summit. The surface is dull, non-reflective, and on cold mornings a thin layer of condensation forms on the exterior, droplets that gather and run in slow, irregular trails down the metal skin. At the base of the silo, there is a rectangular hatch with a small glass porthole. And through this porthole, if you kneel and press your face close to the glass, you can see the interior. The walls are lined with heating coils, copper tubing wrapped in tight spirals that glow faintly orange in the darkness. The air inside is thick and warm, shimmering with convection currents that distort the view. The floor of the silo is not visible. It is submerged beneath 11,000 gallons of molten paraffin, a pale, milky sea that stretches from wall to wall. The pump continues. The hose trembles slightly with the pressure of the flow, a rhythmic vibration that travels from the truck to the valve to the underground pipe. Minutes pass. The sound does not change. It is constant, unwavering, a mechanical heartbeat that fills the Kong between the buildings. Inside the silo, the level of the wax begins to rise. It does not pour or splash. It simply swells, slowly, imperceptibly, the surface lifting 1 millimeter at a time. The heating coils maintain the temperature at exactly 147 degrees. If the temperature drops below 145, the wax will begin to solidify, forming a crust on the surface that will thicken and harden and eventually clog the discharge pipes. If the temperature rises above 150, the molecular structure of the paraffin will degrade, and the final product will be brittle and prone to cracking. A sensor embedded in the south wall of the silo monitors the level of the liquid. It is a simple device, a float attached to a calibrated rod, and as the wax rises, the float rises with it, sending an electrical signal to a control panel mounted on the exterior wall. The panel displays a single number, updated every 3 seconds. A digital readout that tracks the volume in gallons. The driver stands beside the truck watching the hose. He does not check his phone. He does not smoke or pace or speak. He simply waits, his hands in his pockets, his breath visible in the cold morning air. The sky above is the color of concrete, a flat, uniform gray that offers no indication of the sun's position. The only movement is the faint rising of vapor from the silo's ventilation duct, a thin white plume that dissipates almost immediately in the still air. After 43 minutes, the pump begins to slow. The sound changes, dropping in pitch, the hydraulic groan becoming softer, more labored. The hose relaxes, its surface no longer taut, and the vibration that ran through it diminishes to a faint tremor. The driver returns to the valve and rotates the discharge lever back to its original position. The flow stops. Silence returns, sudden and complete, broken only by the distant hum of the heating coils inside the silo. He disconnects the hose. A small amount of wax drips from the coupling, falling in thick, slow drops onto the concrete, where it cools rapidly, solidifying into translucent white beads. He replaces the bronze cap on the valve, turning it clockwise 7 full rotations, and coils the hose back onto its hook. He climbs into the cab, closes the door, and the engine roars to life. The truck pulls away slowly, its tires crunching on the gravel, and within minutes it is gone, leaving only the faint scent of diesel exhaust hanging in the air. Inside silo number 3, the Paraffin rests. The surface is perfectly still, a flawless plane of pale liquid that reflects nothing. The heating coils glow softly, their warmth radiating outward in invisible waves, maintaining the precise temperature required for storage. There is no sound, no motion, only the patient, endless stillness of material waiting to be transformed. The silo will hold this wax for 17 hours. During this time, suspended particles will settle to the bottom, drawn down by gravity, leaving the upper layers clear and homogeneous. At 9 o'clock the following morning, a valve at the base of the silo will open, and the wax will be drawn through a filtration system consisting of 3 stainless steel mesh screens, each with a pore size of 50 microns. But that is tomorrow. For now, there is only storage, only waiting. A second truck arrives. Its engine idles in the same spot, its driver performs the same movements, the hose is connected to a different valve, and the process begins again. This time the wax flows into silo number 1. The sound is identical. The duration is identical. The temperature is identical. By noon, 4 silos have been filled. They stand in a row, 4 aluminum cylinders risen from the earth, each containing 11,000 gallons of molten paraffin, each heated to 147 degrees. The control panels on their exterior walls display their volumes in glowing green numerals. The ventilation ducts release thin streams of vapor that twist upward and vanish. And inside, in the warm darkness, the wax waits, patient and inert and ready. Chapter 2. The Melting Vats. The vats are cylindrical, stainless steel, 32 feet in diameter. Each one holds 11,000 pounds of paraffin wax in block form. The blocks are white, opaque, stacked in irregular columns that reach halfway up the interior wall. They do not move, they wait. The heating elements are embedded in the floor of each vat, coiled resistance wire encased in copper tubing arranged in a grid pattern that spans the entire base. When the current is applied, the metal begins to warm. Not quickly, not suddenly. The temperature rises at a rate of 0.3 degrees Fahrenheit per minute. You can see the first change at the bottom of the stack, where the white paraffin touches the warming steel. The edge softens, the molecular structure loosens. The solid becomes less solid. A bead of translucent liquid forms at the corner of the lowest block. It clings there, suspended, trembling slightly from the vibration of the heating coil beneath. The bead grows heavier. Gravity pulls at it. Eventually, it detaches. It falls, 3 inches. It lands on the steel floor with no sound. It spreads outward in a thin, colorless film. The film is warm, 108 degrees Fahrenheit. More beads form. The blocks are weeping now. Dozens of small rivulets trace down the sides of the paraffin columns. The wax is crying itself into liquid. Each rivulet moves slowly, viscous, thick as honey in winter. They pool at the base. The pools merge. A shallow lake of molten paraffin begins to form across the bottom of the vat. The heating elements do not change their output. They maintain 135 degrees Fahrenheit. No more, no less. This is the target temperature. The temperature at which paraffin wax transitions fully from solid to liquid without degradation. A thermocouple embedded in the center of the vat measures the ambient heat. It sends a signal to the control panel every 4 seconds. The control panel adjusts the current by microamperes if necessary. The system is precise, relentless, indifferent. The blocks are shrinking. As the outer layers melt away, the remaining solid wax appears smaller. The columns that once reached 4 feet high are now 3 feet, then 2. The surface of each block becomes glossy, wet-looking. Light reflects off the thin layer of liquid clinging to the solid core. The liquid wax at the bottom of the vat is now 6 inches deep. It is perfectly still. No ripples, no movement except the slow addition of new liquid from above. The surface is mirror smooth, reflecting the overhead industrial lights in long, distorted streaks. Occasionally, a bubble rises from the bottom. Trapped air, heated and expanding, pushes upward through the thickening pool. It breaks the surface with a soft blip. The sound is absorbed immediately by the dense, warm air inside the vat. Then silence again. Then the hum. Always the hum. The blocks continue to diminish. They lose mass at a predictable rate. 17 pounds per hour per square foot of exposed surface area. The melting is uniform. There are no hotspots, no areas where the wax liquefies faster. The heat distribution is engineered to be flawless. By the second hour, the blocks are half their original size. They sit like islands in a shallow sea of their own dissolved material. The liquid is now 12 inches deep. The weight of the liquid presses down on the heating elements. The steel floor conducts the warmth evenly. The temperature of the liquid wax is measured continuously. 135.2 degrees, 135.1, 135.3. The variation is minimal, acceptable, ignored. The remaining blocks are now irregular shapes, no longer the clean rectangular solids they were when loaded. Melting has rounded their edges, smoothed their corners. They look organic, like stones worn by water over centuries. But this erosion happens in hours, not centuries. The air above the vat is warmer now. Heat radiates upward from the surface of the liquid wax. It rises in invisible columns. The ventilation system pulls this warm air away. Ducts overhead draw it out at a rate of 4,000 cubic feet per minute. The air is replaced with cooler air from vents near the floor. The cycle is constant, necessary, mechanical. By the third hour, only small fragments of solid wax remain. They float now, buoyant in the liquid that surrounds them. Each fragment is no larger than a dinner plate. They drift slowly across the surface, pushed by convection currents too subtle to see. The liquid wax is now 18 inches deep, 11,000 pounds of material now fully transitioned to liquid state. consistency is like thin motor oil. Viscosity measured at 42 centistokes. It flows. It moves, but slowly, with resistance. The final fragments of solid wax are melting. Their edges blur. They become translucent, then transparent. Then they are gone, dissolved into the homogeneous pool. There is no solid material remaining. The vat is now filled with liquid paraffin wax. Clear, warm, waiting. The heating elements continue to maintain temperature, 135 degrees Fahrenheit. The thermocouple sends its signal. The control panel listens, adjusts, maintains. A pump activates beneath the vat. It is a centrifugal pump, stainless steel impeller, three-phase motor running at 1750 revolutions per minute. The pump draws liquid wax from the bottom of the vat through a 4-inch diameter pipe. The flow rate is calibrated, 60 gallons per minute. Not faster, not slower. The liquid wax enters the pipe. It travels downward first, then horizontally beneath the factory floor. The pipe is insulated, wrapped in fiberglass batting 1 inch thick, covered with aluminum foil to reflect radiant heat inward. The wax must not cool during transport. It must remain liquid. The pump runs continuously. The sound is a low, steady throb. Hydraulic pressure pushing against viscous resistance. The motor hums, the impeller spins, the wax flows. Inside the vat, the level of liquid wax begins to drop. Slowly, imperceptibly at first. 18 inches, 17.9 inches, 17.8. A level sensor mounted on the interior wall tracks the descent. It reports to the control panel. The panel does nothing. This is expected. This is correct. The heating elements remain active. Even as the liquid is removed, the temperature must be maintained. The remaining wax stays at 135 degrees. The thermocouple measures. The control panel adjusts. The cycle does not stop. The surface of the liquid wax is still. Despite the pump drawing from below, there is no visible disturbance above. The liquid is too viscous, the flow too gentle. The surface remains a perfect glassy plane. Minutes pass. The level continues to fall. 16 inches, 15, 14. The pump does not change speed. 60 gallons per minute. Constant, reliable, predictable. The overhead lights reflect differently now. As the liquid level drops, the angle of reflection changes. The streaks of light shift position on the surface. Slowly, like the hands of a clock too large to perceive in real time. The vat will empty over the course of 4 hours. This is the designed cycle time. When the level reaches 2 inches, the pump will disengage. The heating elements will deactivate. The vat will cool. The residual wax will solidify. It will be scraped out manually. Returned to raw material. Remelted in the next cycle. But for now, the wax flows. Warm, clear, moving through insulated pipes toward the pigment mixing station. The vat hums. The pump throbs. The temperature holds. Everything continues. Everything is as it should be. Chapter 3. The Pigment Infusion. The vat contains molten paraffin wax. The temperature is maintained at 160 degrees Fahrenheit. The wax is clear. It has the appearance of mineral oil. The surface is still. Above the vat, a hopper holds the pigment powder. The powder is dry. It is a ferric oxide compound. The particles measure between 0.3 and 0.8 microns in diameter. The color is orange, a deep rust orange. The hopper gate opens. The mechanism is pneumatic. There is a soft hiss of compressed air. The gate slides 3 millimeters to the left. Powder begins to fall. The pigment enters the wax as a thin stream. It falls in a continuous column. The column is approximately 4 millimeters wide. The powder does not dissolve immediately. It sits on the surface of the wax for 1.2 seconds. Then it begins to sink. The powder descends slowly through the clear liquid. It forms a vertical plume. The plume expands as it falls. Individual particles separate from the column. They drift outward. They tumble. The orange color spreads in 3 dimensions. The mixing blade has not yet engaged. The wax remains still. The pigment collects at the bottom of the vat. It forms a dense layer. The layer is approximately 2 centimeters thick. The orange is concentrated here. It appears almost brown in its density. More powder continues to fall from the hopper. The stream is constant. The rate of delivery is 15 grams per second. The hopper empties slowly. The process is designed to be gradual. Now the motor engages. The motor is a 3-phase induction type. It produces a low hum. The frequency is 60 Hz. The mixing blade begins to rotate. The blade is mounted on a vertical shaft. The shaft descends from the center of the vat lid. The blade itself is positioned 30 centimeters below the surface of the wax. It rotates at 40 revolutions per minute. This is considered a slow speed. The blade has 4 arms. Each arm extends 20 centimeters from the central shaft. The arms are angled at 15 degrees from horizontal. As the blade turns, it pushes the wax outward and downward. The first rotation disturbs the layer of pigment at the bottom of the vat. The dense orange sediment lifts slightly. It begins to swirl. The movement is circular. It follows the path of the blade. A vortex begins to form. The center of the vortex is directly beneath the shaft. The wax spirals downward into this center. The pigment is drawn into the spiral. Orange tendrils rise from the bottom. They twist as they ascend. The tendrils are thin. They resemble smoke. They curve and fold upon themselves. The wax around them remains clear. The contrast is visible, clear and orange. The boundary between them is soft. The blade completes its second rotation. More pigment is lifted. The tendrils grow thicker. They reach higher into the clear wax. The vortex deepens. The hopper continues to release powder. The stream of pigment falls into the center of the vortex. It is pulled downward immediately. It is drawn into the circulation. The powder no longer sits on the surface. It is consumed by the motion. The mixing process is hypnotic. The orange spreads in slow waves. Each rotation of the blade pulls more color into suspension. The wax near the blade becomes becomes cloudy. It is no longer clear. It is no longer fully orange. It is a transition state. The temperature remains constant, 160 degrees Fahrenheit. The heat keeps the wax in liquid form. The viscosity is low enough to allow the pigment to disperse, but it is high enough to slow the process. The mixing is not rapid. 3 minutes have passed since the motor engaged. The bottom third of the vat is now orange. The middle third is a gradient. The top third remains mostly clear. The blade continues to turn. The vortex is more pronounced now. The surface of the wax dips toward the center. The depression is shallow, approximately 5 millimeters deep. The edges of the depression are smooth. Pigment particles collide with each other in the wax. They do not clump. The formulation includes a dispersing agent. The agent coats each particle. It prevents aggregation. The particles remain individual. They remain suspended. The blade passes through the same volume of wax again and again. Each pass redistributes the pigment. Orange from the bottom is carried to the middle. Clear wax from the top is pulled downward. The gradient slowly equalizes. 5 minutes have passed. The hopper is now empty. The pneumatic gate closes. There is another soft hiss. The stream of powder stops. All of the pigment is now in the vat. The blade continues to rotate. 40 revolutions per minute. The motor hums. The sound does not change. The rhythm is mechanical. It is unchanging. The color in the vat becomes more uniform. The tendrils are no longer visible. The wax is cloudy throughout. It is a pale orange, not yet opaque, not yet the final color. 7 minutes have passed. The top layer of wax begins to change color. The clear liquid becomes tinted. The tint is faint. It is barely perceptible, but it is present. The gradient continues to flatten. The difference between the top and bottom becomes less pronounced. The orange deepens in the upper regions. The orange lightens slightly in the lower regions. The system moves toward equilibrium. The blade encounters resistance from the thickening suspension. The motor compensates automatically. The torque increases by 2%. The speed remains constant, 40 revolutions per minute. 10 minutes have passed. The wax is now a single color. It is orange throughout the vat. The surface is orange. The bottom is orange. The middle is orange. The color is uniform. But the mixing does not stop. The blade continues to turn. This is a safety margin. The process is designed to ensure complete dispersion. Even though the color appears uniform, the mixing continues. 12 minutes have passed. The vortex remains stable. The surface depression is unchanged, 5 millimeters deep. The wax circulates in the same pattern, downward at the center, outward at the bottom, upward at the walls, inward at the surface. The temperature remains 160 degrees Fahrenheit. Heating elements in the vat walls maintain this temperature. The elements cycle on and off. Each cycle lasts 90 seconds. The temperature fluctuates by less than 1 degree. 15 minutes have passed. The mixing protocol approaches completion. The blade has completed 600 rotations. The pigment has been evenly distributed. Every cubic centimeter of wax contains the same concentration of ferric oxide particles. The motor begins to decelerate. The speed decreases from 40 revolutions per minute to 30, then to 20, then to 10. The vortex weakens. The surface depression becomes shallower. The blade stops. The motor disengages. The hum ceases. The wax continues to move for several seconds. Momentum carries it in a slow rotation. The motion decays gradually. The vat is now still. The wax is orange. The color is deep and saturated. It is opaque. The surface is smooth. There is no vortex. There is no motion. The pigment infusion is complete. The clear paraffin wax has become a monochromatic pool of heavy orange liquid. The transformation is total. What was transparent is now opaque. What was colorless is now colored. The vat will remain at temperature. The wax will remain liquid. It waits for the next stage of the process. It waits in stillness. Chapter 4. The Rotary Mold. The liquid wax moves now toward the rotary table. It flows through a heated manifold pipe. The pipe is stainless steel. The interior surface is mirror smooth. The wax maintains a temperature of 185 degrees Fahrenheit. It does not cool. It does not solidify. It remains liquid. The rotary table is circular. It is made of aluminum alloy. The diameter is 48 inches. The surface is flat. The surface is machined. The tolerance is 0.005 inches. Across this surface there are holes. Many holes. Thousands of holes. Each hole is cylindrical. The diameter of each hole is 0.3125 inches. This is 5/16 of an inch. The depth of each hole is 3.625 inches. The holes are arranged in concentric circles. The innermost circle contains 64 holes. The next circle contains 72 holes. The next circle contains 80 holes. The pattern continues outward. The total number of holes is 1,216. Each hole is identical. Each hole is a void waiting to be filled. The metal between the holes is 0.1875 inches thick. This is 3/16 of an inch. The metal is cool. The metal is gray. The rotary table begins to turn. It rotates on a central bearing. The bearing is a sealed ball bearing assembly. The rotation is clockwise. The speed is 0.4 revolutions per minute. This is very slow. One complete rotation takes 2 minutes and 30 seconds. The motion is continuous. The motion is smooth. As the table rotates, it passes beneath the filling station. The filling station is stationary. It is mounted above the table on a steel frame. The frame does not move. The table moves beneath it. The filling station contains a manifold. The manifold is rectangular. It is 6 inches wide. It extends from the center of the table to the outer edge. Along the bottom of this manifold, there are nozzles. 16 nozzles. Each nozzle corresponds to one radial line of holes in the table. As the holes pass beneath the nozzles, they are filled. The liquid wax emerges from the first nozzle. It flows downward. The stream is continuous. The diameter of the stream is 0.125 inches. The wax is the color that was mixed in the blending tank. Perhaps it is crimson. Perhaps it is cobalt blue. Perhaps it is forest green. The color does not matter to the machinery. The stream contacts the surface of the rotating table. For a moment it flows across the flat metal surface. Then a hole arrives beneath the stream. The liquid wax finds the opening. It falls into the void. It fills the cylindrical space. The filling happens in silence. There is no splashing. There is no turbulence. The wax descends smoothly. It flows along the walls of the hole. The walls are smooth. The walls are vertical. The wax coats the interior surface. A thin film forms. Then the volume fills. The level of wax in the hole rises. It rises at a constant rate. The rate is determined by the flow rate from the nozzle. The flow rate is 0.8 fluid ounces per second. The hole reaches half full. The wax continues to pour. The hole reaches 3/4 full. The wax continues to pour. The hole reaches the top. The surface of the wax in the filled hole is level with the surface of the table. There is no overflow. The nozzle has already moved on. The rotation of the table carries the filled hole away from the filling station. Another hole arrives beneath the nozzle. The process repeats. All 16 nozzles operate simultaneously. At any given moment, 16 holes are being filled. The pattern is radial, one hole from each concentric ring. The wax flows. The table rotates. The holes fill. The rhythm is mechanical. The rhythm is absolute. Inside each hole, the liquid wax begins to cool. The aluminum table is cooler than the wax. The table is maintained at 70 degrees Fahrenheit. This is 115 degrees cooler than the wax. Heat transfers from the wax to the metal. The transfer is conductive. The metal absorbs the thermal energy. The wax at the bottom of each hole cools first. It is in direct contact with the metal. The molecules slow. The molecular motion decreases. The paraffin chains begin to crystallize. The phase change is gradual. Liquid becomes semi-solid. Semi-solid becomes solid. The solidification front moves upward through the wax. It progresses from the bottom toward the top. The rate of progression is 0.02 inches per minute. This is slow. The entire cooling cycle takes approximately 3 minutes. During these 3 minutes, the table continues to rotate. The filled hole moves away from the filling station. It travels around the circumference of the circle. As the hole travels, the cooling continues. The surface of the wax develops a skin. The skin is thin. The skin is matte. Below the skin, the wax is still warm, still semi-liquid, but the skin is solid. The color of the wax changes slightly as it cools. If the wax is yellow, it becomes a deeper yellow. If the wax is blue, it becomes a more saturated blue. The pigment concentration remains constant, but the opacity increases. The solid wax is less translucent than the liquid. There are 1,216 holes in the table. At any moment, some holes are empty. Some holes are being filled. Some holes contain cooling wax. Some holes contain fully solidified wax. The distribution is consistent. The pattern repeats. The table continues its rotation. 0.4 revolutions per minute. 150 seconds per revolution. The bearing beneath the table operates without sound. There is a faint vibration. The vibration is transmitted through the steel mounting frame. The frequency is 12 Hertz. This is below the threshold of human hearing, but it can be felt. The manifold above the table does not move. The nozzles remain in fixed positions. The wax flows through them continuously. The pressure in the manifold is constant, 18 pounds per square inch. This pressure is maintained by the pump in the blending tank. The pump operates continuously. The flow never stops. Each nozzle has a valve. The valve is solenoid controlled. The solenoid receives signals from a timing circuit. The timing circuit is synchronized with the rotation of the table. A sensor detects the position of the holes. When a hole is directly beneath a nozzle, the valve opens. When the hole has moved past, the valve closes. The timing is precise. The precision is 0.02 seconds. The symmetry of the process is absolute. Each hole receives the same volume of wax. Each hole experiences the same cooling rate. Each hole produces the same result. 1,216 identical cylinders. 1,216 potential crayons. The filled holes continue their journey around the table. They move through the cooling zone. The cooling zone occupies 270 degrees of the circle. This is 3/4 of the circumference. In this zone, nothing happens. The wax simply cools. The table simply rotates. Time passes. The cooling is passive. There are no fans. There are no refrigeration coils. The heat dissipates naturally into the surrounding air. The air in the factory is maintained at 68 degrees Fahrenheit. The humidity is 42%. These conditions are constant. The cooling rate is therefore constant. By the time a filled hole completes 3/4 of a rotation, the wax inside is fully solid. The temperature has dropped to 75 degrees Fahrenheit. This is 5 degrees above ambient. The wax has contracted slightly during cooling. The contraction is 0.8%. This means the solid wax no longer completely fills the hole. There are small gaps between the wax and the metal walls. The gaps are approximately 0.003 inches wide. The table continues to rotate. The filled holes approach the extraction station. The extraction station is located 90 degrees past the filling station. Here, the solidified crayons will be removed. But for now, they remain in their holes. They are still. They are silent. They are waiting. The rotation continues. 0.4 revolutions per minute. The bearing turns. The table turns. The holes turn. The filled holes move. The empty holes move. Everything moves at the same speed. Everything moves in the same circle. More holes arrive at the filling station. More wax pours down. More holes are filled. The cycle repeats. It has repeated thousands of times today. It will repeat thousands of times tomorrow. The machine does not tire. The machine does not deviate. The surface of the rotary table reflects the overhead lights. The reflection is dull. The aluminum has a brushed finish. Between the filled holes, the metal surface is clean. There is no spillage. There are no drips. The wax goes only where it is directed. Inside each hole, the wax has taken the shape of the void, cylindrical, smooth-walled. The top surface is flat. The bottom surface is flat. The sides are parallel. These are the geometric properties of a crayon. Before labeling, before packaging, before use. The table completes another rotation. 150 seconds have elapsed. During this time, 16 holes have been filled. 16 crayons have been formed. The table begins its next rotation. The process continues, uninterrupted, mechanical, rhythmic. The symmetry persists. 1,216 holes, arranged in concentric circles, each hole identical, each hole waiting, each hole empty, then filled, then solidified, then extracted, then empty again. The rotation does not stop. The filling does not stop. The cooling does not stop. The circle turns. The wax flows. The holes fill. Again, and again, and again. Chapter 5. The water coolant. The water arrives cold. It enters the system at 14 degrees Celsius, pulled from a reservoir tank positioned 3 meters below the factory floor. The pump that moves this water operates at a constant rhythm, a low hydraulic pulse that repeats every 1.3 seconds. The sound is not loud. It is a muffled pressure, felt more than heard, transmitted through the steel framework of the cooling table. The pipes are copper. Each pipe measures 12 millimeters in diameter, running in parallel channels beneath the mold surface. The interior walls of these pipes are smooth, worn slightly by years of continuous flow, but still efficient. Water moves through them at a rate of 4 liters per minute, a flow that never varies, controlled by a valve calibrated to maintain consistent pressure. Above the pipes, separated by only 6 millimeters of machined steel, the wax rests in its mold cavities. The wax arrived hot, 68 degrees Celsius. Now it begins to lose that heat. The steel conducts the warmth downward, molecule by molecule, transferring thermal energy to the metal, and the metal transfers it to the water flowing beneath. The first 30 seconds are critical. In this window, the outer surface of each crayon begins to solidify. The paraffin molecules, which were loose and chaotic in their liquid state, begin to align. They form crystalline structures, hexagonal lattices that interlock, creating the smooth skin that will define the crayon's final surface. This skin forms at a rate of approximately 0.2 millimeters per second, spreading inward from the contact point with the mold. Beneath the table, the water absorbs this heat. Its temperature rises, not dramatically, 0.3 degrees per minute, but the system compensates. The heated water exits through an outlet pipe, returns to the reservoir, where it disperses into a larger volume, cooling passively before being cycled back. The loop is continuous. Water enters cold. Water exits warm. The factory floor never stops this exchange. There is a sound, a faint ticking. It begins around the 45-second mark. This is the sound of the mold itself contracting, Steel contracts when it cools, and though the change is microscopic, measured in micrometers, it produces a quiet metallic tick. The sound repeats irregularly, every 8 to 12 seconds, as different sections of the mold table respond to the temperature gradient. The ticking is sharp, but dry. Not an echo, just a brief release of tension in the metal. Inside the crayon mold, the transformation continues. After 1 minute, the outer shell is solid, but the core remains liquid. This creates a pressure differential. As the outer wax solidifies, it contracts slightly, creating a hollow void that the liquid core fills. The process is self-regulating. The wax flows inward, settling into the space left by the contraction, ensuring no air pockets form. The cooling continues. 2 minutes. The solidification front has moved inward, now occupying 60% of the crayon's volume. The remaining liquid at the center is still warm, still mobile, but it is losing heat at a predictable rate. The copper pipes beneath continue their work. Water flows. Heat transfers. The cycle does not pause. There is no visible change on the factory floor. The molds sit still. The overhead lights cast the same even illumination. But beneath the surface, the molecular architecture of the wax is rearranging itself. Liquid becomes solid. Chaos becomes order. The process is thermal, governed by the laws of thermodynamics, mediated by the patient flow of cold water. At 3 minutes, the crayon is 80% solid. The core is still soft, but it no longer flows freely. It has reached a gel state, where the paraffin molecules are partially aligned, but not yet locked into their final configuration. This state is temporary. It lasts approximately 40 seconds before the remaining heat dissipates and the gel transitions to a true solid. The water temperature in the outlet pipe has stabilized. It now measures 16.2 degrees Celsius, exactly 2.2 degrees warmer than the inlet temperature. This differential is constant. It represents the heat load being removed from the molds, a continuous extraction of thermal energy, measured in joules per second, but experienced as a simple flow of cool water. The ticking has slowed. The mold table is approaching thermal equilibrium. The metal no longer contracts rapidly. Instead, it settles into a stable temperature, close to the temperature of the water flowing beneath. The ticking now occurs once every 20 to 30 seconds, a residual adjustment, a final alignment of the steel's internal stresses. 4 minutes. The crayon is now solid throughout. The core has crystallized. The temperature at the center of the crayon is now 32 degrees Celsius, well below the paraffin's melting point. The transformation is complete, but the cooling does not stop. The water continues to flow. The mold continues to extract heat, bringing the crayon closer to room temperature, ensuring that when it is removed, it will not deform or soften. The pump continues its rhythm, 1.3 seconds between pulses. The sound is unchanged. The pressure in the pipes is stable. The flow rate remains at 4 liters per minute. This consistency is the foundation of the process. Without it, the cooling would be uneven. The crayons would solidify at different rates, creating variations in density, imperfections in surface finish. But the water does not vary. It flows, and the crayons cool uniformly. 5 minutes. The mold is ready to be opened, but before that occurs, the cooling system performs one final function. It ensures that the mold surface itself is cool enough to be touched, cool enough that the next batch of liquid wax, when poured, will encounter a thermally stable environment. The water flowing beneath the mold is not only cooling the crayons, it is also resetting the mold, preparing it for the next cycle, maintaining the rhythm of production. There is no drama in this process, no sudden change. The water arrives cold, the water leaves warm, the wax arrives hot, the wax becomes solid. The exchange is patient, governed by the rate at which molecules transfer their kinetic energy, mediated by the conductivity of copper and steel, controlled by a pump that never hesitates. The reservoir tank beneath the factory floor holds 600 liters of water. It is a large rectangular container made of galvanized steel, with baffles inside to prevent sloshing. The water inside this tank is never still. It circulates constantly, drawn up through the pump, pushed through the cooling pipes, returned to the reservoir, where it disperses, cools, and begins the cycle again. The temperature of the reservoir water fluctuates slightly during peak production, when multiple mold tables are operating simultaneously. The reservoir temperature can rise to 18 degrees Celsius. During quieter periods, it drops back to 14. But these fluctuations are gradual, absorbed by the large thermal mass of the water itself. The system is self-buffering. No external chiller is needed. The volume of water is sufficient. The sound of the water is almost inaudible. Inside the pipes, it produces a faint rushing, a susurration that blends with the ambient noise of the factory. If you place your hand on the side of a copper pipe, you can feel a slight vibration, a tremor transmitted through the pipe wall by the flowing water. The vibration is smooth, consistent, lacking any turbulence. This indicates laminar flow, the ideal state for efficient heat transfer. 6 minutes. The crayon has now reached 28 degrees Celsius. It is cool to the touch. The wax has contracted fully. The crystalline structure is stable. There will be no further dimensional changes. The cooling process, from a thermal perspective, is complete, but the water continues to flow. The system does not know when a single crayon is ready. It operates on a timer, a fixed interval, ensuring that every mold receives the same cooling duration, regardless of minor variations in initial temperature or wax composition. The copper pipes will last for years. Copper does not corrode easily in contact with fresh water. Over time, a thin layer of copper oxide forms on the interior surface, but this layer is protective, preventing further degradation. The pipes require no maintenance. They are inspected annually, but rarely replaced. The system is robust. The pump that drives this system is a centrifugal design. An electric motor spins an impeller at 1,750 rotations per minute. The impeller, made of stainless steel, accelerates the water outward, creating a pressure differential that drives the flow through the pipes. The motor consumes 300 watts of electrical power. It runs continuously during production hours, 8 hours per day, 5 days per week. Its bearings are sealed and lubricated for life. The expected service interval is 15,000 hours. 7 minutes. The mold is opened, but beneath, the water continues to flow. It does not pause for the removal of finished crayons. It does not wait for the next batch of liquid wax. It simply flows, maintaining the mold temperature, ready to begin the cycle again. The cycle repeats. A new batch of wax is poured. The wax contacts the cool mold surface. Heat begins to transfer. The water beneath absorbs this heat. The temperature rises 0.3 degrees per minute. The wax begins to solidify. The outer shell forms. The core remains liquid. The ticking begins again as the metal contracts. The process is identical to the one before, and the one before that, and the one that will follow. This is the work of the water, invisible, beneath the surface, a continuous extraction of heat, a patient transformation of liquid to solid, regulated by flow rate and temperature, maintained by a pump that never stops, flowing through pipes that never clog, returning to a reservoir that never empties. The factory floor is quiet. The molds sit in rows. The overhead lights hum at 60 cycles per second, and beneath it all, the water flows. Cold water in, warm water out. The rhythm never changes. The crayons cool. The cycle continues. Chapter 6. The Ejection. The mold has cooled. The wax inside has contracted slightly, pulling away from the steel walls by micrometers. There is a faint creaking sound as the metal frame settles, releasing stored thermal tension. The temperature has dropped to exactly 73 degrees Fahrenheit. The wax is now solid, completely solid, rigid. A hydraulic valve opens somewhere beneath the mold table. You cannot see this valve. It is buried in the machinery, but you can hear the pressure building. A low hiss, then a deeper hum as fluid moves through chambers. The sound is steady, mechanical, predictable. The ejector plate begins to rise. This plate sits directly beneath the mold cavities. It is made of brushed aluminum. Its surface is perforated with thousands of small pins. Each pin aligns perfectly with the base of a crayon cavity. The hydraulic pressure pushes upward at a rate of 3 millimeters per second. Slow, controlled, constant. The pins make contact with the bottom of each crayon. There is resistance. The wax has adhered slightly to the mold walls despite the release agent. The hydraulic system compensates. Pressure increases by 0.4 bar. The pins continue upward. You hear a faint crackling sound. Thousands of tiny separations happening simultaneously. Wax releasing from steel, molecule by molecule. The crayons begin to emerge. At first, only the tips are visible, small conical points rising above the surface of the mold. They appear in rows, perfectly aligned. Red crayons in column A, blue crayons in column B, yellow crayons in column C. The pattern repeats across the entire mold surface. 100 columns, 50 rows, 5,000 crayons rising together. The ejector plate continues its upward motion. The crayons rise further. Now you can see the shoulders, the point where the conical tip transitions to the cylindrical body. This transition is smooth, gradual, The wax surface catches the overhead fluorescent light. It reflects in bands, horizontal lines of brightness moving across each crayon as it rises. The effect is uniform, repetitive, hypnotic. The hydraulic hiss becomes louder. The system is nearing maximum extension. Fluid pressure holds steady at 6.2 bar. The ejector pins push upward until each crayon is elevated exactly 12 millimeters above the mold surface. This is the optimal height, high enough for the collection mechanism to engage, not so high that the crayons become unstable. The crayons stand in formation, 5,000 vertical cylinders, each one perfectly parallel to its neighbors. The spacing between them is uniform, 8 millimeters center to center. They do not touch. They do not lean. They simply wait, supported by the pins beneath them, motionless, silent. Above the mold, a robotic arm begins to move. This arm is mounted on a gantry system. 2 parallel rails run the length of the production line. The arm travels along these rails on wheels, precision bearings, sealed against dust. The movement is smooth. There is a faint whirring sound. Electric motors driving timing belts. The arm moves at a speed of 20 centimeters per second, approaching from the left side of the mold. The arm extends downward. It has 3 joints: shoulder, elbow, wrist. Each joint articulates independently. Servo motors provide precise angular control. The arm lowers until the end effector is positioned 2 centimeters above the tops of the crayons. It pauses. Sensors verify the position. Optical sensors. They emit infrared light and measure the reflection. The system confirms alignment. The end effector is a vacuum gripper. It consists of a rectangular plate, 30 centimeters wide, 50 centimeters long. The underside of this plate has 100 small suction cups. Each cup is made of soft silicone, black silicone, flexible, durable. The cups are arranged in a 10 by 10 grid, matching the spacing of the crayons below. A vacuum pump activates. The pump is located in the base of the robotic arm. It draws air through plastic tubing. The tubing runs through the arm joints. Flexible tubing, reinforced to prevent collapse. Air pressure inside the tubing drops to negative 0.8 bar. The suction cups contract slightly. Their edges become concave, ready to seal against the surface of the crayons. The gripper descends. It moves downward at a rate of 5 millimeters per second, slower than before, more cautious. The suction cups make contact with the tops of 100 crayons. The silicone compresses. It forms an airtight seal around each crayon tip. The vacuum holds. Negative pressure creates adhesion force, approximately 50 grams per crayon, enough to lift, not enough to deform the wax. The gripper begins to rise. The robotic arm retracts upward. Servo motors engage. The crayons are pulled from their ejector pins. There is a soft popping sound, 100 small separations. The crayons release cleanly. No sticking, no residue. They hang suspended from the vacuum cups, vertical, motionless. The arm moves horizontally. It travels along the gantry rails, moving away from the mold, toward a collection tray positioned 3 meters to the right. The crayons sway slightly during transit, a pendulum motion, small oscillations dampening over time. The vacuum holds them securely. They do not fall. The collection tray is made of white plastic, high-density polyethylene. Its surface is divided into compartments. Each compartment corresponds to a crayon color. Red compartment, blue compartment, yellow compartment. The tray is empty, waiting to receive the first batch. The robotic arm positions the gripper above the appropriate compartment. The crayons hang 10 centimeters above the tray floor. The vacuum pump deactivates. Air pressure equalizes instantly. The suction cups release. 100 crayons drop simultaneously. They fall in parallel, vertical trajectories. Impact occurs after 0.14 seconds. The sound is a collective clatter, wax striking plastic, a brief percussion, then silence. The crayons settle in the compartment. Some land upright. Others fall on their sides. They roll slightly. Friction stops the motion within 2 seconds. They come to rest against each other, overlapping. Random orientations, but confined within their designated space. The robotic arm returns to the mold. It follows the same path in reverse, 20 centimeters per second. The gantry wheels turn. Bearings rotate smoothly. The arm repositions above the next section of crayons. The vacuum pump activates again. The gripper descends. Suction cups make contact. Another 100 crayons are lifted. The cycle repeats. Back at the mold, the ejector plate remains elevated. The pins still extend upward, supporting the crayons that have not yet been collected. 4,900 crayons remain, standing in formation, waiting. The overhead lights cast small shadows. Each crayon shadow falls at a precise angle, determined by the position of the fluorescent tubes. The shadows do not move. They are fixed, static. The robotic arm makes its second pass. It lifts another 100 crayons, transports them to the collection tray, releases them, returns to the mold. The motion is identical to the first pass. Same speed, same trajectory, same sounds. The whirring of motors, the hiss of the vacuum, the soft pop of crayons releasing, the clatter of impact. This process continues. The arm moves back and forth, methodically. Each cycle takes 18 seconds, 12 seconds for transit and positioning, 4 seconds for vacuum activation and gripping, 2 seconds for release and return initialization. The timing is precise, controlled by a programmable logic controller, digital timers, millisecond accuracy. After the third pass, 300 crayons have been collected. The collection tray is beginning to fill. Crayons accumulate in layers. The bottom layer is compressed slightly by the weight of subsequent layers. Wax deforms minimally, less than 0.1 millimeter, imperceptible to the human eye, but measurable. The robotic arm continues its work. Fourth pass, fifth pass, sixth pass, each pass identical to the last. The rhythm is unbroken. The machine does not tire. It does not pause. It simply executes its programmed sequence over and over, without variation. On the mold surface, the forest of crayons is thinning. Rows are being cleared from left to right. Empty cavities appear, dark voids where crayons once stood. The ejector pins retract into these empty cavities. Hydraulic pressure releases incrementally. As each section is cleared, the corresponding pins lower back to their resting position. The descent is slow, 2 millimeters per second. Gravity assists the motion. The collection tray is now half full. 2,500 crayons rest inside. The colors are separated. Red in one compartment, blue in another, yellow in a third. The boundaries between compartments are maintained. No mixing occurs. The tray design prevents spillover. The robotic arm continues. 26th pass, 27th pass, 28th pass. The repetition is absolute. There is no deviation. The machine follows its instructions with perfect fidelity. Each movement occurs at the exact moment specified. Each position is achieved with sub-millimeter precision. Finally, the 50th pass is completed. All 5,000 crayons have been transferred. The mold is empty. The ejector plate has fully retracted. The pins rest flush with the bottom of the mold cavities. Hydraulic pressure returns to zero. The system idles, waiting for the next mold to arrive on the conveyor. The collection tray is full. Crayons are piled within their compartments. The surface is uneven, random peaks and valleys. Some crayons stand vertical, others lie horizontal. Many are at oblique angles, but all are contained. None have escaped. A conveyor belt activates beneath the collection tray. The tray begins to move. It slides forward at a speed of 10 centimeters per second, heading toward the next station, the labeling station. But that is another process. For now, the ejection is complete. The robotic arm returns to its home position. It retracts fully. The gripper rises to the top of its travel range. The arm moves to the far left of the gantry. It parks there. Motors disengage. The system enters standby mode, waiting for the next cycle to begin. Chapter 7. The Paper Jacket. The wrapping station receives the cooled crayons in a continuous stream. Each crayon arrives at precisely 18 degrees Celsius. The conveyor belt moves at a constant velocity of 4.2 meters per minute. The crayons roll slightly as they travel, their waxy surfaces catching the overhead fluorescent light in dull, matte reflections. The paper itself comes from an industrial roll mounted on a horizontal spindle. The roll weighs 43 kilograms. The paper is a wood pulp composite, calendared to a thickness of 0.08 millimeters. The surface has been pre-printed with the brand markings, the color name, and the regulatory information in 6-point sans serif type. The unwinding mechanism applies a constant back tension of 12 newtons. This prevents the paper from telescoping or wrinkling as it feeds into the machine. A series of 3 guide rollers, each covered in nitrile rubber, direct the paper web toward the cutting station. The rollers rotate at synchronized speeds, their bearings emitting a low, mechanical hum that resonates at approximately 120 Hertz. The guillotine blade descends every 1.4 seconds. It is a hardened steel edge, honed to a bevel angle of 22 degrees. The blade cuts through the paper web with a brief, pneumatic whisper. Each severed rectangle measures exactly 11.3 centimeters in length. The width is 4.1 centimeters. The tolerances are held to plus or minus 0.2 millimeters. A vacuum pickup head descends immediately after each cut. 6 small apertures on the pickup face create negative pressure. The vacuum intensity is calibrated to 14 kilopascals. This is sufficient to lift the paper rectangle without deforming its surface. The pickup head rises, traverses laterally 3.6 centimeters, and rotates 90 degrees clockwise. The paper now hovers above the wrapping mandrel. The mandrel is a cylindrical steel shaft. Its diameter matches the crayon diameter precisely, 7.9 millimeters. The surface is knurled with a diamond pattern, each knurl depression measuring 0.3 millimeters deep. This texture provides grip for the rotation mechanism. The mandrel is driven by a servo motor capable of delivering 0.8 Newton-meters of torque. A crayon is fed horizontally onto the waiting mandrel. Pneumatic fingers guide it into position. The crayon slides forward until it contacts a mechanical stop. The stop is a simple steel pin, 3 millimeters in diameter, positioned to ensure the crayon's tip extends exactly 1.5 millimeters beyond the mandrel edge. The vacuum pickup releases the paper rectangle. It descends and drapes across the waiting crayon. The paper's leading edge is coated with a thermoplastic adhesive. The adhesive is a polyvinyl acetate emulsion, applied in a stripe exactly 2 millimeters wide. The adhesive layer is 30 microns thick. It has been warmed to 48 degrees Celsius by an infrared heating element positioned 6 centimeters upstream. The mandrel begins to rotate. The initial acceleration is smooth, reaching full speed in 0.3 seconds. The rotational velocity stabilizes at 420 revolutions per minute. As the mandrel spins, the paper wraps around the crayon in a tight, controlled spiral. The sound is distinctive, a rapid, repeating zip, zip, zip. The paper edges create friction against the crayon's waxy surface. This friction generates a high-frequency vibration, approximately 3,000 hertz. The vibration propagates through the machine frame, creating a faint, metallic resonance. A pressure roller descends during the rapid cycle. The roller is covered in soft silicone, durometer rating 40 Shore A. It applies a contact force of 6 newtons along the length of the crayon. This pressure compresses the adhesive layer, forcing out microscopic air bubbles, ensuring a smooth, intimate bond between paper and wax. The glue smells faintly sweet. The polyvinyl acetate releases trace amounts of acetic acid during curing. The concentration is below 3 parts per million, but perceptible in the warm air circulating through the wrapping station. The odor mingles with the scent of fresh paper, which carries notes of lignin and cellulose, earthy and slightly acidic. The wrapped crayon completes one full rotation. The trailing edge of the paper meets the adhesive-coated leading edge. A secondary pressure roller, positioned at the overlap point, applies 15 newtons of force for exactly 0.2 seconds. This creates a lap seam, 3 millimeters wide, running parallel to the crayon's longitudinal axis. The mandrel decelerates. The servo motor applies regenerative braking, recovering kinetic energy and feeding it back into the power supply. The deceleration curve is linear, taking 0.4 seconds to reach a complete stop. The wrapped crayon remains stationary on the mandrel for 0.6 seconds. This dwell time allows the adhesive to achieve its initial tack. Ejector pins extend from within the mandrel. There are 2 pins, positioned 180 degrees apart. Each pin has a hemispherical tip, 1.5 millimeters in diameter. The pins extend 4 millimeters, pushing the wrapped crayon off the mandrel with a soft, mechanical click. The ejected crayon falls 12 centimeters. It lands on a padded conveyor belt. The belt surface is a closed-cell foam, 2 millimeters thick, designed to cushion the impact and prevent damage to the paper wrapper. The landing produces a muffled thump, dampened and nearly inaudible beneath the ambient machine noise. The cycle repeats. Another crayon arrives on the mandrel. Another paper rectangle is cut. The vacuum pickup descends. The paper drapes. The mandrel spins. Zip, zip, zip. The wrapping station processes 84 crayons per minute. This translates to 1.4 crayons per second. Over the course of an 8-hour shift, the machine wraps 40,320 crayons. The paper roll must be replaced every 6 hours. Replacement takes 3 minutes. During this interval, unwrapped crayons accumulate in a small buffer zone upstream. The machine operator monitors a control panel. The panel displays real-time data, mandrel speed, paper tension, adhesive temperature, wrapping count. The operator notes any deviation from standard parameters. Adjustments are made via a touchscreen interface. Most shifts require fewer than 5 adjustments. The adhesive temperature is critical. If it drops below 45 degrees, the bond strength decreases. The paper may separate from the crayon during subsequent handling. If the temperature exceeds 52 degrees, the adhesive becomes too fluid. It seeps beyond the intended adhesive stripe, creating visible staining on the paper surface. The infrared heater consumes 120 watts. It uses a tungsten filament enclosed in a quartz tube. The filament glows a dull orange, emitting radiation primarily in the near-infrared spectrum, between 700 and 1400 nanometers. The radiation is absorbed by the adhesive's polymer chains, causing them to vibrate and generate heat. The paper passes beneath the heater for exactly 1.2 seconds. This exposure time raises the adhesive temperature from ambient 22 degrees to the target 48 degrees. A thermocouple embedded in the guide roller measures the paper temperature continuously. Feedback from the thermocouple adjusts the heater output, maintaining thermal stability to within 1 degree. Each wrapped crayon exits the station with a perfectly aligned seam. The seam is positioned at the 6 o'clock position, relative to the crayon's longitudinal axis. This orientation is maintained by a mechanical indexing pin, which engages a small notch cut into the mandrel surface. The pin ensures that every crayon is wrapped identically, seam in the same location, overlapping in the same direction. The sound continues. Zip, 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 a rhythmic, mechanical pulse. The frequency never wavers. 1.4 hertz. Constant. Predictable. Hypnotic. The wrapped crayons travel downstream toward the inspection station. The padded conveyor belt moves at the same 4.2 meters per minute. The crayons roll slightly as they travel, their paper wrappers rustling softly against the foam surface. The rustling is a dry, fibrous sound, textured and granular. A vision system photographs each crayon. The camera captures images at a resolution of 2000 by 2000 pixels. The frame rate is synchronized to the conveyor speed, 1.4 frames per second. Image processing algorithms analyze the wrapper alignment, seam position, and print quality. Crayons with defects are ejected by a pneumatic blast. The rejection rate is typically below 0.5%. Most defects involve adhesive seepage or paper misalignment. Rejected crayons are diverted to a collection bin. The bin is emptied once per shift. The defective crayons are unwrapped manually, and the bare wax cylinders are returned to the melting vats for reprocessing. The mandrel rotates again. The paper wraps. The glue warms. The seam bonds. The pins eject. The crayon falls. Zip, zip, zip. The air in the wrapping room is warm. The ambient temperature is maintained at 24 degrees. This ensures consistent adhesive performance. The humidity is controlled at 45% relative humidity. Lower humidity would cause the paper to become brittle. Higher humidity would soften the paper, making it prone to tearing during the wrapping cycle. Ventilation fans circulate the air at a rate of 6 complete air changes per hour. The fans are centrifugal units, each powered by a 3-phase induction motor. The motors produce a low, steady drone, approximately 100 Hertz, blending with the mechanical hum of the wrapping machines. The process continues without interruption. Each crayon receives its paper jacket. Each wrapper is applied with identical precision. The rhythm is unbroken. Zip, zip, zip. Chapter 8. The Sorting Bin. The crayons fall, one by one. They release from the conveyor belt's edge and drop into the collection bin below. The distance is 47 centimeters. Gravity pulls each crayon downward at a rate of 9.8 meters per second squared. The fall takes approximately 310 milliseconds. Then comes the impact. The first crayon of this particular cycle strikes the galvanized steel bottom of the bin. The impact produces a sharp, metallic tap. The sound frequency peaks at 4,200 Hertz. The crayon bounces. It rises 6 centimeters from the bin floor, rotates 40 degrees along its longitudinal axis, and falls again. The second impact is softer, 3,800 Hertz. The crayon settles into a horizontal position, rolling slightly until friction between the wax surface and the steel arrests its motion. The second crayon falls. It is red number 70. Its mass is 8.3 grams. It strikes the first crayon at an angle of 22 degrees. The collision creates a duller sound, wax on wax. The acoustic profile is broader, less resonant. 2,100 Hertz. Both crayons shift. The first crayon rolls 3 centimeters to the left. The second crayon comes to rest perpendicular to the first, forming an imperfect cross shape at the bottom of the bin. The third crayon is yellow number 12. It falls. 310 milliseconds. It strikes the junction where the first two crayons meet. The impact disperses. Energy transfers into three separate vectors. All three crayons shift. The yellow crayon wedges itself into the angle created by the red and the first crayon. The sound is muffled. 1900 Hertz. The bin now contains 3 crayons. The total mass is 24.7 grams. The fourth crayon falls. Blue number 33. It strikes the yellow crayon near the tapered end. The yellow crayon rotates 11 degrees. The blue crayon does not bounce. It slides along the smooth wax surface of the yellow crayon for 2.4 centimeters. Then comes to rest against the side wall of the bin. The metallic wall is cool, 18.6 degrees Celsius. The blue crayon surface temperature is 21.3 degrees. Heat begins to transfer from the wax to the steel. The transfer rate is 0.04 joules per second. The fifth crayon falls. Green number 58. 310 milliseconds. Impact. It lands atop the intersection of the first 3 crayons. The structure beneath it compresses slightly. Wax is a viscoelastic material. Under load, it deforms. The deformation is 0.02 millimeters, imperceptible to the unaided eye, but measurable. The green crayon settles into a stable configuration. 5 crayons now rest in the bin. The sixth crayon is orange number 19. It falls. The trajectory is identical. 47 centimeters, 9.8 meters per second squared, 310 milliseconds. The orange crayon strikes the green crayon. The sound is a low wooden clatter, 1600 hertz. The impact causes the green crayon to tilt. Its angle shifts from horizontal to 14 degrees from horizontal. The orange crayon rolls. It descends the slight incline created by the tilted green crayon, traveling 8 centimeters before coming to rest in the corner of the bin. The seventh crayon falls. Purple number 41. The bin now contains a growing lattice of crayons. The purple crayon strikes this lattice near the center. The impact distributes across 4 contact points. The sound is complex. Multiple frequencies overlap. 2000 hertz, 1700 hertz, 1400 hertz. The purple crayon does not settle immediately. It rocks, back and forth. The rocking diminishes. Each oscillation is smaller than the last. After 2.6 seconds, the motion ceases. The 8th crayon falls. Brown number 82. 310 milliseconds. It strikes the purple crayon. Both crayons shift. The lattice reorganizes. The brown crayon slides into a gap between the purple crayon and the blue crayon. The fit is snug. The brown crayon is now wedged. It cannot move without external force. The bin contains 8 crayons. Total mass is 66.4 grams. The 9th crayon is pink number 27. It falls. The conveyor belt above continues its forward motion at 12.7 centimeters per second. Each crayon reaches the belt's edge at regular intervals. The interval is 1.9 seconds. The pink crayon drops. 47 centimeters. 310 milliseconds. Impact. The pink crayon lands on the periphery of the crayon lattice. It strikes the steel floor of the bin. 4100 hertz. A sharp tap. The pink crayon bounces. 7 centimeters. It rotates 53 degrees. It falls again and settles. The 10th crayon falls. Black number 99. The lattice is denser now. The probability of a crayon striking steel decreases with each addition. The black crayon strikes the pink crayon. Wax on wax. 1,800 Hertz. The black crayon does not bounce. It rolls. 5 centimeters. It comes to rest against the brown crayon. 10 crayons. 83 grams. The 11th crayon is white number 6. It falls. 1.9 seconds have elapsed since the previous crayon. The rhythm is constant. Fall. Impact. Settle. Fall. Impact. Settle. The white crayon strikes the black crayon at the midpoint. The sound is dull. 1,500 Hertz. The white crayon tilts. It balances atop the black crayon at an angle of 31 degrees from horizontal. Gravity pulls it downward, but friction between the two wax surfaces holds it in place. The coefficient of friction is 0.42. The 12th crayon falls. Gray number 65, 310 milliseconds. The gray crayon strikes the tilted white crayon. The white crayon loses its balance. It slides down the surface of the black crayon. The slide takes 1.1 seconds. The white crayon comes to rest horizontally. The gray crayon lands in the space the white crayon previously occupied. The lattice adjusts. 12 crayons, 99.6 grams. The 13th crayon is red number 71. It is identical in composition to red number 70. Paraffin wax, stearic acid, red pigment suspension. The 13th crayon falls. 47 centimeters, 310 milliseconds. Impact. The red crayon strikes the gray crayon. 2,000 Hertz. The red crayon bounces slightly. 3 centimeters. It falls back and wedges itself between the gray crayon and the orange crayon from earlier in the sequence. The 14th crayon falls. Yellow number 13. The bin is approaching 1/4 capacity. The steel walls are 60 centimeters tall. The current layer of crayons is approximately 11 centimeters deep at the deepest point. The yellow crayon falls. 310 milliseconds. It lands atop the lattice. The impact creates a muted thud. 1,300 Hertz. The yellow crayon does not roll. It is supported on 3 sides by other crayons. It remains in place. The cycle continues. The conveyor belt moves at its constant speed, 12.7 centimeters per second. Crayons arrive at the edge, 1.9 seconds apart. Each crayon falls the same distance, 47 centimeters. Each crayon accelerates at the same rate, 9.8 meters per second squared. Each fall takes 310 milliseconds. The variation is negligible, plus or minus 3 milliseconds. The 15th crayon is blue number 34. It falls. Impact. 1,600 Hertz. The 16th crayon is green number 59. It falls. Impact. 1,700 Hertz. The 17th crayon is orange number 20. It falls. Impact. 1,800 Hertz. The sounds blend. A continuous percussion, irregular in pitch, but regular in rhythm. The bin fills slowly. Each crayon adds 8.3 grams on average. Some crayons are slightly heavier, 8.5 grams. Some are slightly lighter, 8.1 grams. The variation is due to minor inconsistencies in the molding process. 1/10 of a gram here, 2/10 of a gram there, over thousands of crayons. The average converges on 8.3 grams. The 18th crayon is purple number 42. It falls. The lattice beneath is now 14 centimeters deep at the center of the bin. The purple crayon's fall is shorter, 33 centimeters instead of 47. The fall time decreases, 260 milliseconds. The impact velocity is lower, 2.5 meters per second instead of 3.04 meters per second. The sound is softer, 1,200 hertz. The 19th crayon is brown number 83. The 20th crayon is pink number 28. The 21st crayon is black number 100. They fall in sequence. 1.9 seconds, 1.9 seconds, 1.9 seconds. The rhythm does not waver. The machinery above is indifferent to the contents of the bin. It delivers crayons at a fixed rate. The bin receives them. The crayons continue to fall. 22, 23, 24. Each impact creates a sound. Each sound is absorbed into the ambient noise of the factory, the hum of motors, the hiss of hydraulics, the distant clatter of other sorting bins receiving their own streams of crayons. The sound of this bin is one thread in a larger acoustic tapestry. The bin will continue to fill. At the current rate of 1 crayon every 1.9 seconds, the bin will reach capacity in approximately 47 minutes. Capacity is defined as 1,500 crayons. At that point, a sensor at the rim of the bin will detect the height of the crayon pile. The sensor will send a signal. The conveyor belt above will redirect its output to the next bin in the sequence. This bin will be removed. The crayons will be transported to the packaging line. But that moment is still 44 minutes away. For now, the crayons fall. They strike. They settle. The lattice grows denser. The pile grows taller. The rhythm continues, unchanging, predictable, mechanical. Chapter 9. The Final Box. The robotic arm extends from its mounting point on the overhead gantry. The servo motors engage with a faint electrical hum. Metal joints articulate in programmed sequence. The gripper mechanism descends toward the completed crayon bundle. Pneumatic pressure builds within the actuator cylinder. Compressed air forces the piston forward at precisely regulated velocity. The gripper fingers spread to their maximum aperture of 8.2 centimeters. Silicone pads on the inner surface of each finger provide non-slip contact. The bundle consists of 24 crayons arranged in 4 rows of 6. Each crayon weighs 4.8 grams. The total bundle mass is 115.2 grams. The gripper closes around the bundle perimeter with calibrated force. Pressure sensors in the gripper pads detect contact. Feedback loops adjust compression to prevent deformation. The wax bodies of the crayons remain undamaged. Paper wrappers maintain their cylindrical grip on each wax core. The arm lifts the bundle vertically. Acceleration begins at 0.3 meters per second squared. Maximum velocity reaches 0.5 meters per second. The bundle rises through still air in the assembly facility. Yellow cardboard boxes wait on the conveyor belt below. Each box measures 22 centimeters in length. Width spans 9 centimeters. Height measures 7 centimeters when folded closed. The cardboard consists of bleached kraft paperboard. Thickness measures 0.4 millimeters. The material exhibits a smooth matte finish on the exterior surface. Compression strength rated at 200 kilopascals. The boxes arrive pre-folded from the forming station. Bottom flaps interlock in a tucked configuration. Side panels stand vertical, creating an open rectangular cavity. Top flaps remain unfolded, pointing outward at 90-degree angles. The robotic arm rotates through its horizontal axis. Movement follows a parabolic trajectory path. The bundle travels through three-dimensional space toward the waiting box. Deceleration begins 1.2 seconds before arrival. The gripper positions the bundle directly above the box opening. Descent occurs at reduced velocity of 0.1 meters per second. The lowest crayon tips enter the cardboard cavity. Clearance between bundle edge and box wall measures 2 millimeters on each side. The bundle settles against the box bottom. Cardboard fibers compress slightly under the distributed weight. The gripper fingers release pneumatic pressure. Silicone pads retract from contact with the crayon surfaces. The robotic arm withdraws vertically from the box interior. The bundle remains stationary within the cardboard container. 24 crayons rest in their designated positions. Paper wrappers display color names in black sans serif typography. A secondary arm mechanism approaches from the perpendicular axis. This arm carries a rectangular cardboard insert. The insert measures 21.5 centimeters by 8.5 centimeters. Printed graphics display the product logo and color chart. The insert descends into the box. It slides past the crayon tips with minimal clearance. Friction between cardboard surfaces produces a soft whisper of contact. The insert settles horizontally across the top of the crayon bundle. A third mechanical assembly engages with the box top flaps. Flat metal guides contact the outer flap surfaces. Motorized actuators push the flaps inward toward the box centerline. Each flap rotates downward through 90 degrees. The longer flaps fold first. They extend from the box ends, spanning the full width. Cardboard creases along the scored fold lines. Compression creates microscopic fractures in the paper fiber matrix. The shorter side flaps fold over the longer flaps. Overlap creates a double layer of cardboard across the box top. Interlocking tabs slide into corresponding slots. Friction holds the closure without additional fasteners. Light within the box interior diminishes as the flaps close. Illumination decreases from full ambient brightness to shadow. The final gap between flaps narrows to 0. Complete darkness envelops the crayon bundle. The crayons rest motionless in absolute blackness. No photons penetrate the sealed cardboard barrier. Temperature inside the box equals ambient facility temperature of 18 degrees Celsius. Air remains still with no convection currents. The conveyor belt beneath the box resumes motion. Rubber belt material grips the cardboard bottom surface. The box slides forward, at constant velocity of 0.2 meters per second. Vibration from the belt motor transmits through the box structure. Inside the sealed darkness, the crayons maintain their positions. Wax cores remain solid at current temperature. Molecular bonds in the paraffin chains hold stable. Paper wrappers continue their protective function. The box travels along the conveyor toward the palletizing station. Distance measures 43 meters. Transit time calculates to 215 seconds. The belt moves with mechanical consistency. Other boxes follow in sequence behind. Each box contains an identical arrangement of 24 crayons. Each box travels the same path on the same belt. The process repeats without variation. The box edges remain sharply folded as it moves. Cardboard maintains structural rigidity. Yellow exterior surface shows no marking or damage. Printed graphics remain clearly visible. Inside the darkness, the crayons experience no change. They do not shift position during transport. The cardboard insert above them prevents vertical movement. Box walls prevent horizontal displacement. The palletizing station consists of a stationary platform and a mechanical stacker. The platform measures 1.2 meters square. Surface height sits at floor level. Material composition is reinforced composite polymer. The box approaches the platform edge. A sensor beam detects the box presence. The conveyor belt halts motion. The box rests stationary at the transfer point. A pusher arm extends from the side of the conveyor. Metal blade contacts the box edge. Horizontal force pushes the box sideways off the belt. The box slides onto the pallet platform. Friction between cardboard and platform surface slows the box. The box comes to rest in a designated position. Alignment sensors verify correct placement. Position accuracy maintains tolerance of plus or minus 3 millimeters. The next box arrives and occupies the adjacent position. Box edges align parallel with minimal gap. The pattern builds in rows of 6 boxes. Each row contains 144 crayons in total darkness. 5 rows complete the first layer. 30 boxes occupy the pallet surface. 720 crayons rest in sealed containers. The layer forms a stable rectangular array. A cardboard separator sheet descends from an overhead dispenser. The sheet measures 1.2 meters by 1.2 meters. Thickness matches the box material at 0.4 millimeters. The sheet settles flat across the completed box layer. The second layer begins. Boxes slide onto the separator sheet. The same pattern repeats. 6 boxes per row. 5 rows per layer. The pallet grows vertically. Layer 3 positions above layer 2. Layer 4 above layer 3. Each addition increases total pallet height by 7 centimeters. 10 layers complete the pallet stack. 300 boxes occupy the vertical column. 7,200 crayons exist in sealed darkness. Total pallet height reaches 70 centimeters plus base height. The boxes in the lowest layer bear the compressive load of all layers above. Cardboard structure distributes weight evenly. No deformation occurs in properly stacked configuration. The bottom boxes maintain their rectangular form. Inside these bottom boxes, the crayons remain in absolute darkness. They experience slight increase in ambient pressure from the stacking load. Wax remains solid. Temperature holds constant. A wrapping machine encircles the completed palette. Transparent polyethylene film unrolls from a motorized dispenser. The film width measures 120 centimeters. Thickness measures 25 micrometers. The palette rotates on a turntable mechanism. Angular velocity maintains 0.1 radians per second. Film wraps in overlapping spiral pattern. Each rotation adds another layer of transparent barrier. Film tension remains constant at 15 newtons. Stretch ratio equals 130%. Polymer molecules align along the tension axis. Elastic recovery creates compressive hold on the box stack. The wrapping continues for 12 complete rotations. Film layers accumulate around the palette perimeter. Visual clarity diminishes with each additional layer. The yellow boxes become progressively more obscured. Inside the innermost boxes, darkness persists unchanged. The crayons know nothing of the wrapping process. Their sealed environment admits no light. Their temperature remains stable. The completed palette moves to the warehouse staging area. A forklift approaches with hydraulic hum. Fork tines slide beneath the pallet base. Hydraulic cylinder extends, lifting the entire assembly. The warehouse interior spans 50 meters by 80 meters. Ceiling height reaches 12 meters. Lighting consists of overhead fluorescent fixtures spaced at 3-meter intervals. Floor surface is sealed concrete with epoxy coating. The forklift transports the pallet down a numbered aisle. Aisle width measures 4 meters. Storage racks line both sides, extending to full ceiling height. Each rack position holds one pallet. The pallet arrives at its designated storage location. Rack position number 7-3-B. Third level elevation. Middle position in the aisle sequence. The forklift mast extends vertically. Hydraulic pressure overcomes gravitational load. The pallet rises to match the rack shelf height. Alignment occurs within tolerance specifications. Fork tines retract, sliding the pallet onto the storage shelf. Metal shelf surface supports the pallet weight. The pallet settles into final resting position. Motion ceases completely. The forklift withdraws and departs. Sound of hydraulic systems fades into the warehouse distance. Silence returns to aisle 7. The pallet rests motionless on its shelf. Inside the boxes, darkness continues absolute and unchanged. 7,200 crayons wait in sealed containers. No light reaches them. No sound disturbs them. Temperature in the warehouse holds at controlled 18 degrees Celsius. This temperature penetrates slowly through the cardboard barriers. The wax cores gradually equilibrate to ambient conditions. Thermal equilibrium requires approximately 40 minutes. The crayons rest in their precise manufactured arrangement. 4 rows of 6, each color in its designated position, each wrapper printed with its specific name. In the darkness, these details remain invisible. The colors produce no photons. The wrapper text cannot be read. Everything exists in potential waiting for future illumination. The warehouse operates on a 24-hour cycle. During night hours, the overhead lights extinguish. Emergency lighting maintains minimal illumination. The aisles become darker, though never completely black. For the sealed crayons, this external change means nothing. Their darkness remains absolute regardless of external conditions. Day and night hold no distinction. They wait in unchanging obscurity. Time passes in the silence of the warehouse. The pallet remains stationary. The boxes maintain their stacked configuration. The crayons rest undisturbed in their paper wrappers. Eventually, a new forklift will arrive. Fork tines will slide beneath the pallet. Hydraulic lift will raise the assembly. Transport will begin toward the shipping dock. But for now, there is only stillness. Only darkness inside the boxes. Only silence in the warehouse aisle. Only waiting.